I see trees of green.
I tried to make the point last week that the science of forestry is just a tool that you can use any way you like. So I'm going to go right back to the inherent how a tree grows and then ask the question, like you talked about why you wanted to grow them last week. We're going to say, how can we manipulate that growth? Because we really have a couple of options, and many people love the term or use the excuse, I'm just going to plant them and let nature take its course. And I rebel against that for a number of reasons. And the primary reason is that nature doesn't know where it's going, and it doesn't know what's coming in that sense. And people are starting to appreciate that because we know the climate's changing, we know the vegetation doesn't know what's about to hit it with regard to temperature increases. But the other point is, if you just plant trees and walk away, they do not by some magical way get to some pristine forest condition that is optimum for that location and the wildlife and the products or anything you want to produce it for. So having identified why you want to do it, we're saying you're an active participant. You're a master tree grower. You're the one who's going to take that forest in that particular direction, whatever your motivations. And I referred that our little forest that I spend my summer in, which is in a national park, apparently being managed for biodiversity and recreation. It's not very good for biodiversity because of the way it's been managed in the past. It could be better, and just locking it up is not going to make it better, in my view. And we'll talk about that. The great thing about being private landholders, we can largely use these tools to direct the growth in the ways we want to go. And that's what I'm particularly enthusiastic about. I wouldn't be able to get far in government because all the other opinions about how Crown land would be managed are dominant over the view that I have, so I work with private landholders. So we're going to give you a diameter tape. It's the same as if you're a cattle farmer measuring pasture. Everyone says you can't manage what you don't measure and stuff like that. So, and the exercise are giving you a tape. Now rip your tape open, take the masking tape off. And we'll go through this tape today, and we're going to use it to measure all the sort of technical things I want to talk about this morning. And hopefully we can measure it, and what particularly Tony's going to show us, monitor growth over a period of time. And that gives us confidence that we're taking the forest or the trees in the right direction, and the potential to see how we can manage them more effectively. So in this tape, which is on the yellow side, a normal metric ruler 2 metres long. That's your sewing tape. Okay? On the white side, it says, if you look at the Master TreeGrower logo, then it says 0, and then it says made in Germany, and I move along to about 4, it says diameter in centimetres and millimetres. So if I wrap this tape around my belly,
that's brave.
publicly, on the yellow side, I'm going to call it a worry. 103, isn't it supposed to be less
Are
than
you allowed
100?
to cheat on your trees like you do on your waste?
On the other side, much nicer number, 33. 33. Like a tree, I cannot measure through my body and get an average diameter of my trunk. This works out the diameter. And I'll leave that with you because the more mathematically minded will know how it does that, but I'll show you in a moment. We give you this tape also, if I can speak on behalf of my profession, and this is where I have been in trouble before. The Master TreeGrower course, when I set it up, I wanted to hand over the science and language of forestry to the farming community. I got a lot of trouble for that. My boss at university, who's now passed, he called me into his office one day, the professor of forestry, sat me down and held up this piece of paper to himself and said, "The Consulting Foresters Association want me to shut you down." So what's going on? And he said, "You're handing out Masters of Forestries in 8 days. That's taken them years to get, and they're the consultants, they know." And he was deadly serious, and I thought, well, this is it. You know, the Master TreeGrower is dead after 2 years. And then he smiled and laughed. and said he was a member of the Consulting Foresters Association. And he agreed with me that we're actually doing more for the Consulting Foresters Association than not, because we're showing them what foresters know. So a little bit of knowledge is likely to raise more questions in your mind, and also, I hope, give you a great appreciation for what other experts or experienced people might actually be able to help you with. And that, I hope, is the outcome as well. So in handing over the tape, we're saying to you, we believe that you are capable of using the technical aspects of forestry to help you do what you want to do with the trees. So if we look at a single tree, that's a Queensland kauri in a plantation up in central Queensland. I love that tree. I've started planting it. It grows really big in gardens in Melbourne and produces a lovely pale timber. Queensland kauri, like New Zealand kauri. New Zealand kauri is a bit nicer on the timber side. But if you look at that, we can measure a diameter at different points up the tree, and generally they'll get smaller as we go up. We can measure the height of that tree. We can assess the form. Now I call that perfect, nice and straight, but that's just a forester in me. If you're looking at it from a different perspective and saying form to you is whether it's got a big hollow in it or whether it's shading the right place in the paddock, so you'll have your own judgment. So form. We can look at the branches, where they are and how big they are on the stem. If branches are either a positive or negative, for your particular. We can look at taper. Taper is how fast it gets smaller as we go up the stem. And growth rate. If we measure diameter once, come back and measure it again, that difference is a really useful tool. And Tony's going to show us some graphs of the trees we're looking at. Because if you can see what's happening year to year, just by putting a tape around a tree, the knowledge is really important in my view. Then the other point is to take a whole forest. We talked about an individual tree. We've got these certain measurements we can take for that. At a forest level, we've got some other things we can look at. The average diameter of the trees. We might have 50 trees. We can look at the average height. We can look at volume per hectare, number of trees per hectare. We start having these measures that don't pertain to the individual, but pertain to the whole forest. It might be how many different species there are, the ratio of different species on that forest. So all these things come into play by putting the individual information together and having some description of the forest itself. And again, we've done today. And if you measure the volume per hectare twice, or anything average diameter over a period of time, you can get change again. And measuring change is really what's quite powerful. So diameter is our first point. To use a convention, which is basically the old 4 foot, 1.3 metres, we agree to all measured trees at what we call breast height. Now New Zealand, when they went metric, said 1.4. So they're obviously a bit taller than us. But we all agree 1.3. And it doesn't really matter if it's 1.25 or 1.4, because at that part of the tree, there's not going to be a lot of taper. But if you start thinking, I'm going to measure at the base, well, that's really complicated because there's all these buttresses and roots. So we just agreed to make it simple. We all measure at 1.3 above it. And that's boys, a very long time ago, showing you where breast height is on a poplar tree on that property. So that's the first point. We talk about diameter of breast height, and we reduce that down to dBH. Okay, this is a African chief on a farm in just a couple of hours out of Nairobi, and he's measuring an Australian species called silky oak, which I was really interested to find was introduced by Australian development programs during the 60s and 70s, along with eucalypts and casuarinas, to address the fuelwood shortage. And you go back down, and the only species you'll see is the silky oak, because the silky oak was quite weedy, and it wasn't competitive with their coffee and tea crops, so they actually planted it to mark the boundary of their farms by agreement with their neighbour. Now before when they were just food producers, they told me they used to use a local lily for that. But when they started growing shrubs like coffee and fruit trees, that shaded the lily out, so they needed something bigger. Then to stop the competition from those silky oaks, they chopped the branches off and fed them to their goats or sheep or cows, and they ended up with these pruned stems. And during the late 90s, the Kenyan government banned the logging of native forest, and all of a sudden the timber brokers were going up to these farms and saying, we want to buy your silky oak. And they had to negotiate. How do they negotiate when they've got no idea the size of their trees or how to compare the price that one landholder got with another, over and above questions of quality and risks that come into play? So I handed this guy, the chief, who couldn't speak the same language, showed him how to use it, and they were really excited about this idea. We've now got a way of comparing our trees and measuring in some fashion. So he's wrapping the tape down around the tree using the white side, as I showed you before, matching the point up with 0. And so he's wrapping around the circumference, but he's measuring the diameter. And as you all know now, what is the distance between 1 and 2, or 31 and 32? 3.1427 centimetres. Because the number of pies around the circumference is equivalent to the diameter of the tree, because the formula is 2 pi r. 2r is diameter, so it's just how many 3.142s there are around the circumference. So all this tape just does that little bit of mathematics for you, so you can use it to measure the diameter of a culvert or a flagpole or anything like that. It just works out. And the good thing about trees is if you go up with calipers and try to measure diameter, by convention you've got to do at least 2 measurements and take the average, because trees aren't always going to be perfectly circular. This will average out all that little deviation and give you a simple measure. And because it is a nice average at one point, you can put a little bit of paint on that tree, or you can just say, I'm always going to measure it at my breast height from the same side of the tree, and you can go back and re-measure it. The great thing about something like silky oak, you can put a little paint line on that. I do it on my pine trees and some of the others, but eucalypts shed their bark and that falls off, so that's not very useful. So in terms of marking where that point is. So you can re-measure. And calipers, you'll never get the same measurement by 2 people. So it's a really good system to use. Very simple, and so rather than going to the pub and say my trees are about this tall, how fat are they? Don't really know. You'll be able to give a good accurate measure of their diameter of those trees. The basal area is just an area measurement at that point. That's the cross-sectional area of that tree. Now you know that's going to be important as soon as you start talking about volume of trees. You have to work out a cross-section before you can work out a volume. So you can work out the volume of the pipe, you take the cross-section and multiply by its length. Simple. But you know, trees are a bit more complicated because they're not the same diameter as you go up. But this measure I'll talk about today, I like it because it also tells us something about competition in a forest, which we'll talk about later. So from that measurement, we can do on a spreadsheet or just on a calculator, we can work out basal area. And I've got a calculator, we'll stand it, Paddy, we'll just work out some figures. It looks complicated, the formula. Basal area equals diameter divided by 200 squared. That is just the radius of the tree squared. We're talking about pi r squared. To get the radius in metres from a diameter that we measured in centimetres, we're going to divide it by 200. That's all I'm doing there. Squaring it, then multiplying by pi. So that's pi r squared, and you're all familiar with that thing. And so diameter in centimetres and pi 3.1427 or whatever you use for that. So that's what, we've got 2 things, the diameter and basal area just from that tape already. Then I was confronted with, obviously tree height is important. It's important if you're cutting a tree down and you want to know how far away to park the ute, so you don't hit it. And it's obviously important because it also affects volume of the trees, or the amount of shade that you're going to get out into a paddock, or a range of different things. So I was confronted with this idea, how can I measure the height of a tree with a 2 metre long tape? And I remember where I was when it occurred to me. I was actually on the Hume Highway, driving south from up near Benalla, where we had a field day, and I was confronted by this about 20 years ago or so, and said, yes, we can do this, because measuring height is often done with angles, as you know, and they're quite expensive tools. We are getting to the point where our mobile phones can do it,
Mhm.
and I'm excited about that, because they'll actually work out the distance you are away, or you click on it, then you walk away, and using GPS it works out how far back you are. Then you look at the top and the bottom with your mobile phone and work it out. But it's really dependent on how accurate the GPS is. So
Mhm.
obviously that will be a tool, and we're just starting to use that in some of our tree work. But you can do it with this tape, and that's the Master TreeGrower Salute. So this is a group of farmers in southeast Queensland measuring a hoop pine in central Queensland, just a long way away. And that's the key, stand well back, so you've got a clear view of the top and the bottom of the tree. Then they're holding their tape up, so it hangs like that, using the yellow side, so it's got lots of measurements and it's quite easy to follow. Then you move it up and down, so that the bottom of the tape, the 0 mark, corresponds with the bottom of the tree. Close one eye. So if I do that to the wall, I'm just moving it down, so 0 mark is the bottom of the wall. And then you look to the top without moving your head like this, without moving the tape like this, because we're trying to get everything optically nice and accurate. We hold it, I let go for a moment, then pull it, so it's, I hope you can see it's nice and straight. Then without moving my head, I look up, and the wall appears to be 35 centimetres tall. Through my eye from this position. If I then say, I want to know a point on that wall, which is 10% of what it appears to be, I would now do it again, but come up to a point that appears to be 10% of that, or 3.5 centimetres up the tree. So I'll just line that up, 35 at the top, 0 at the bottom. Okay, I need glasses. So it's actually, the top of the PowerPoint is 10% of the height of the wall. So all I've got to do over there is now walk over to the tree, over the tree will be a bit higher up, and measure where 10% is, and that comes out to be 34 centimetres. So that is 3.4 metres, maybe. I'm not going to measure it because it's wrong in front of you all. But, so we've got here a sort of simple way to me to get a pretty good estimate. Now, it is 100% accurate in theory. All the error has to be your error doing this. And of course, I'll walk around when you're trying it today and I'll say, well, that's, you can't do that, you can't do this. So step well back, so you're comfortable with looking at the top and the bottom of the tree, and do that. Another system. So another way of doing it, you probably, you just walk into your forest, pick up a stick, walk back from the tree till the stick is about the height of that. Then if the ground is flat, pretend to fell the tree 90 degrees, and there's a point over there which will correspond to it. Keep your eye on that and then pace it back and get a rough idea of how high the tree is. So it's all the same sort of optical techniques that we can use, whether you're using expensive angles or that, but it's a simple technique. Yep.
We learned one at Scouts that is similar, but it works only if you have sunshine and you measure your shade laying down.
Yep.
Because you know how tall you are. And then you trace back the shade on the ground with your body length.
The reason I like this is that it's not dependent on flat land.
Yeah.
It doesn't matter if you're uphill or downhill from the tree. All that matters is that straight up and down, and the tree is straight up and down. Pretty hard to measure a crooked tree that's leaning away or towards you. You probably wouldn't bother measuring that anyway, because it's that. If a tree's got a broad canopy, remember you're trying to pick a point above the bottom of the tree, not the point you see on the edge. Again, the further away you walk. So it's a sort of simple technique that allows us to measure height. The question is, do you really need a very accurate height measurement? Well, it all depends what you're going to do with that information. If you're looking at change, and it's just for are my trees growing taller, you can sort of start monitoring that. I find that on our property, particularly because I'm more interested in saw logs than total tree height, I'm actually not that interested in height. Although when I fell the trees, I pace out and measure the tree. Because I'm interested in I parked the tractor well away from one during COVID, landed it, and it was just 2 metres short of the tractor, and it was the biggest tree we'd ever harvested, 41.5 metres tall. And I thought, gee, they are getting tall. And they're getting really competitive with the paddocks and stuff. And I'm thinking, well, these eucalypts have to go. If they catch fire, that fire's going to throw further and other aspects like that. As I said before, I'm pretty obsessed about straight trees for my particular interests. And so in our minds, we'll have all different measures depending on what we're doing with our trees. Whether a tree is, I have 3 categories, whether it is perfect, whether it is no good at all, and whether it's somewhere in between. So for our property, when I'm trying to grow a sawlog of a certain distance, perfect will be from the base to the top of where that sawlog is. It's as good as I can likely get for that species. Now I say that because I will tolerate a blackwood that does a little bit of this on the way up, but I probably won't tolerate a redwood that does that, because redwood can be perfect and straight and stuff like that. These ones here, the ones that are roughly saying they're no good for the purpose, primary purpose you're growing the trees, it doesn't mean you're going to kill them all, because you might say, well, I'll keep it for biodiversity or shelter, or because I like the leaf foliage. But you understand that by leaving it, you may be compromising the growth of your products around the tree. So we'll see forests today that have been thinned, and talk about how you actually select the trees that you might remove and which ones you might kill. In between, in some cases, in many cases, you won't have enough perfectly good trees for the job you want. And so you're going to have to keep a few number 2s as well. And we'll talk about what compromises. So maybe they've got a kink in at a certain height, so it's a short log. Maybe they've had a bit of insect attack or a bit of disease, and you don't know what impact that's going to have on their future value or something like that in some fashion. So we talked about volume. We can work out volume, but we have to adopt, as Rita referred to, some sort of theory. We can go and do all the measurements, but some sort of theory about the shape of the tree. Now the easiest one is to adopt, particularly in young eucalypts and pine trees and those Queensland kauris, is that our tree is essentially a cone. It gets thinner as you go up, but on a regular amount. In fact, trees are rarely that. They tend to be what I call a torpedo. Particularly if you prune them, they tend to go up like this, then come in faster at the top. So they tend to have a bit more volume than a cone. So my feeling is by adopting a cone shape as a theory, I'm actually being slightly conservative, which is great. It's always good to not overestimate your volume, particularly if you're anticipating doing some numbers on its value. And we can do that from a height and diameter measurement using the volume for a cone, which is the area at the base of the cone. Now we didn't measure diameter at the base, we measured it up here. I did all these measurements when we did some harvest, and we were measuring diameter up here, but I used the volume estimate for the top of the stump. And it actually worked out really well, because I'm measuring over bark here, but I want under bark down there. And it was a pretty good match. And it was a little bit conservative again, because you tend to have all that buttressing down the bottom of the stem. So don't worry too much, that's only 1.3 metres, and this might be 10, 15 or 30 metres tall. So we're being a bit conservative there, which is good because we measured over bark. Our volume of a cone is the area at the base of the cone times the height divided by 3. So the 3 is the sort of form factor that comes in. If it was a cylinder, it would be form factor 1, basal area times height. And if you look at the people who've done studies, and if you own 1,000 hectares of trees and they're all one species, you'd probably go through and do some mathematical, cut the tree at various heights all the way up and work out your perfect form factor. But when I've looked at those models, they tend to be in the order of 2.7 or something like that. So we're being a little bit conservative, which I think is great. So if a tree is 40 centimetres in diameter and 25 metres tall, it is basically about 1 cubic metre of wood. Just to sort of, what's a cubic metre of wood? I like to think it's a 55 centimetre diameter log about 5 metres long, or it's a 25 metre tall tree, 40 centimetres in diameter. That's about a cubic metre. We'll measure a couple of trees today, and say, well, you need 10 of these to get a cubic metre, but you only need 3 of those. Well, that's a big difference if you're cutting down trees using labour, lifting them up with your farm tractor. If you only have to lift 3 to get a cubic metre compared to 10, well, you can see some economies in there, whether it's for firewood even, and start thinking about that value. And we can do all that with the tape. So we're going to go out this afternoon and talk about that. We'll work out log volume and other aspects. But we're also going to talk about carbon today because Tony and Reid are actually measuring that on their property. And we can use the same basic measurements to work out the carbon in a tree. But I thought I'd just show you, first of all, a block of wood. This is a block of our blue gum, sawn timber that I've dried in the kiln and then stuck 3 pieces together, and all the mathematics that I've put up. I'm just sort of interested, I came up with this demo that the carbon dioxide that was stored in that ball is all locked up in that wood, which is kind of nice if you think about all the carbon dioxide that's come out of the atmosphere, because in wood, all the carbon has to come from the atmosphere. It doesn't come from the carbon in the soil, it's all through photosynthesis, the production of sugars. Some of those are burnt to drive growth, some of them are converted to cellulose to make wood. So when we talk about carbon, there's only more carbon in the tree from year to year if the tree is got more wood in it, it's bigger. A tree that doesn't grow from year to year is balancing the burning of carbon against its consumption. So it's all balanced out. It's locking up as much as it's burning, you're not getting progress. If it's rotting in the middle faster than it's putting on wood, probably going backwards. So it's useful, I think, to think about how much of that we can do that in the sense. So that piece of wood I'm passing around is 10 by 10 by 10, so it's a litre. It weighs, I just put it on the scales and I know the moisture content, 850 grams. So it actually floats, but it floats, it won't sink. You can get blue gum from really some sites that is very dense and will sink at 12%. And we use 12% because you can't, all this wood's got moisture in it. It draws moisture out of the atmosphere and gives it back depending on whether it's humid or dry in the environment. It finds an equilibrium. And in Victoria we say for most uses inside that equilibrium out inside a building it's going to be between 10 and 14%. If you go to the coast in Queensland, it can vary from 8 to 16% because it gets so humid for such a long period of time that the timber will increase. So 12% is a term you'll often hear for air-dried wood density. If I take that water out, I can calculate that the weight would be, without any water, 750 grams. You have to remove the water. There's no carbon in water, and I just want to know what the wood is. The carbon content of wood has been measured for hundreds of different species. Everyone's interested. Take this piece of wood, how much carbon is in it? Carbon is in the cellulose and the lignin. The lignin is the glue that joins the cellulose together. It tends to be between 49 and 51% for all species. So let's just call it 50%. You know that you have long chain carbohydrates in a tree, and carbon, there'll be hydrogen, some oxygens and various other things in there, but it works out about 50%. So the carbon in that block is half that weight, 375 grams, and to work out how much carbon dioxide the tree would have had to suck in order to store that much, we multiply it by 44 over 12. Now who's the chemist who can explain to everyone else why 44 over 12? So the molecular weight of carbon in a molecule, the molecular weight of carbon is 12. The weight of a carbon dioxide molecule is 12 plus oxygen, which is 44. So if we're going to work out what all that is, that's got lots of oxygen as well, we're going to have to convert that. So it works out about 0.8 or a cubic metre, which I worked out is the amount of water, the amount of air, the volume of a big beach ball. I just like that as an analogy and say, let's use it. Lock it up. So I'm trying to actually measure how much carbon we're locking up in our house that we're building, hoping to offset all the carbon that I've emitted in the steel and the concrete. I think we'll be lucky to come out neutral given all the concrete I've been putting in the ground. And we'll talk this afternoon about how you can probably work out for a standing tree how much carbon is there. But these guys have done more of that than I have, so we'll look at that. And we will skip that. The other thing we talked about, this forest is not far away from here. Anyone know what that is? That's Walnut Island. These are black walnut trees that were planted in the early 70s on an island on the Goulburn River, just not far from here. And Hugh Meggett and his family, he bought the property, bought it because they wanted to set up a trout farm, you would have seen there. And the trout farm, they needed access to the river. And by buying the beautiful river flats, he bought 60 hectares of black walnut trees. And he didn't know what they were, well, some deciduous tree. He subsequently found out he was the owner of the biggest black walnut plantation in the southern hemisphere. Went over from America, and they all told him, gee, wow, that's fantastic. He got excited and he was going to make lots of money, but then he found out how slow they grow. And he was focused on his trout. But the trees are still there, and a guy from New Zealand did some thinning trials. He thinned out patches, and you walk through there and occasionally there'll be an opening with less trees in it, because he thinned down to various amounts. And I love that, because we can say, what impact did that spacing, creating a parkland rather than a dense block, what impact did it have on growth? And that's what we're going to talk about today, because that's what I'm really excited about. How can we get in there with a chainsaw or ring barking or anything, or even planting less or doing something more or growing them longer? What impact did that have on the size of the tree, the health of the tree, and its potential to lock carbon up in wood or to produce a useful product in some way? Now, when you've got a forest, we can measure individual trees, but if we want to know how many trees there are per hectare, we need to have a defined area. We'll do that with a square plot or a circular plot, some way of working out we're measuring all the trees in this area. And we call that a sample plot, statistics. And if you've got a large block, you might put in 10 sample plots, and hopefully we're going to see a sample plot today, because that's the way a forest is being measured. So you can measure an individual tree and see how that individual's grown, or you can measure a group of trees on a known plot. And that's great. I've got a couple of spots where I get the students to come back every year and measure. I've just put a steel peg in the ground, I run a tape out 20 metres, and we just re-measure every tree within that 20 metres. And then I've plotted it over time, and they go, well, you've learned something already, just by re-measuring a group of trees. If you measure one, that's great, but how many trees are there per hectare? What impact are they having on each other?
When you thin out, do you take the stumps out? And what difference does that make in the cost of thin out?
Well, we'll talk about that out, because it's going to depend on how those stumps respond.
Yeah.
But personally, I don't. Some of them coppice a little bit, and I just knock the coppice off. But because I'm taking selective trees, they tend to be in the shade of the other ones, and the coppice never really grows well. But there are many examples which you're treating a larger area, you get a lot of coppice regrowth, it becomes a problem, very competitive, a fire threat, and stuff like that. I wouldn't go to the point of digging a stump out for a couple of reasons. First of all, I wouldn't poison the stump either, we'll talk about that. Because that stump may be root grafted to other trees. And I'm now of the view that when you thin half the trees out, you increase the root area for the trees you left, because they're utilising some of the root system that was feeding those other trees.
Yeah.
And that may be why we suddenly get a very rapid response in thinning sometimes, is because we're directing water that used to go up that tree's not there, but the root system's grafted and is going up that tree.
Even if it's dead, it will still...
Well, the stumps don't die, they stay alive. And I'll show you live stumps on outposts on eucalypts, oaks, casuarinas and pines.
But they're not
And
reshooting.
I've got 5 living stumps that I
Not reshooting though.
They're not reshooting.
Still alive, but they don't
Still
reshoot.
alive, you scratch the bark and there's
Okay.
living.
That's really
So we'll talk about that. And we'll also, you might have a plot sheet or some, the data that you collect from the plot, you're going to write down and feed into some computer model. And if you want to do this, we've got some simple Master TreeGrower spreadsheets. I can just email you and say, just put the data in here and it'll give you all the averages, do all the calculations for you and stuff like that. And then you can adapt the spreadsheet to suit it. We'll do that. When I talked about height, I think this is an important point. We're not doing a really accurate measurement of height. And I probably alluded to the fact that that doesn't really matter for a number of different reasons. First of all, when you measure volume, you're multiplying you're squaring the measurement of diameter squared. And so any error is actually multiplied up again. Whereas you measure height, if you're out by 10%, your volume estimate is out by 10%. But if you're out by 10% on diameter, I haven't worked it out, but you're out by a lot more than 10% because you're multiplying that error. So that's one point. And the other thing is, who actually uses height? And what are we using it for? Even if you're selling pulpwood, you can do a rough estimate of total volume, but you're going to get paid not on that measurement, you're going to get paid on what goes across the scales. And on that point, a friend in Western Australia was out there, when they were doing a pulpwood harvesting, he was out there cutting samples and weighing them, and he ran around at lunchtime on a Friday and told the guy to stop harvesting because he found out that over the weekend he was losing weight of water that was drying out. And any wood left on site would be lost money. So he said, stop at lunchtime, go home and go again and get it on the truck as soon as you can on Monday, because I'm being paid for the water because they're measuring the weight. They've made assumptions, but selling dry wood is not good when you're paying. So the thing about height is that the forest, if you've got a similar species, even the same species, but a similar species, growing on a similar soil type, they tend to be all pretty much the same height. Now the way I describe this is that height is about lifting water. And if one of these trees was slightly taller than the ones around it, it would have more trouble lifting water because of the dry air around it. It's missing out on the shelter of its neighbours. So its growth will slow. Whereas the one that's just below the shelter of its neighbours will grow faster because it's in a nice humid environment. So the forest sort of goes like this. And in fact, when it gets to the point that it can't grow anymore in height because it just can't lift water in that environment with that species on that soil type, you'll grow in spring and die back in summer. Grow in spring. You'll see the top of the trees go up and down like this because it's all about lifting water in that environment on that soil. And drying winds and lack of water at the ground, that column of water in the tree, there's probably medical people here, it's like a cavitation, it's like an air bubble in your veins. You can't lift it if there's an air bubble there. And you get these cavitation things resulting from that the tension in that water column. And that stops the water going right up to the top. So in a dry year, you'll see the tops of eucalypts die back a little bit. In most cases, they'll come wood and go again. They'll reach that point again. So,
Rowan, one thing we've seen at Canumba is, because we've got some slopes on there, and the top of the tree, it's almost not horizontal, but the bottom ones are much taller than the ones up the hill.
So the
So it
ones
depends
down
where
the
you
valley
measure
have
it.
got a deeper soil, a bit more water, and a more humid landscape than the ones at the top. And you'll see this with windbreaks. Just drive through the landscape and you'll see same trees planted on the same site, same year, short, tall. And there's not much we can do, as we'll talk about making trees grow taller, except how we shelter each other, how we shelter them when they're young. So we tend to, when I measure a forest, I'm not measuring the individual tree, I'm doing a rough height measurement for the whole forest. I'm ignoring the really tall ones and the small ones and taking what we call a dominant height, the height of the majority of the dominant trees that have got their tops in sunlight. And that's the sort of measurement I'll take, standing back from the whole forest. And that'll give me a good gauge of the average height of that forest. The basal area of the forest, if we had a plot of land and we cut all the trees off at the 1.3 metres and we measured that area of each of those stumps, this was a hectare of land, that would be the basal area per hectare. That is a really useful measurement. You'll see it pop up in the graphs because it combines two things. If you've got 100 trees per hectare and they're small trees, your stocking rate, number of trees per hectare, doesn't change. It's still 100 when it's a year older. Another year it's still 100 if they all survive. So what is actually changing is the area of all those cross sections. So that the basal area is actually increasing. So 100 trees which are small and young, they're growing as if they're out in the open, full sunlight. But as they grow fatter and fatter and fatter, they're going to start shading each other and the competition's going to start. So there is some point in particular species where the basal area gets to a point where competition is slowing down the growth. And that's what you're going to see examples of thinning out to reduce the basal area. of the forest. And you'll see me using various techniques. If we have a plot, we can just add up the basal area of all the trees and work out the area of land, work out the basal area per hectare. Okay? I want to show you the other Master TreeGrower salute, and you won't believe this, but I'm going to show it to you. Don't worry about the theory behind it, call it black magic, but a German forester 110 years ago, I think in the early 1900s, worked out that if you stand in the middle of your trees and hold something that has a known thickness, a known distance away from your eye, and you spin around and you look at all the trees in that forest to count how many look fatter than that little thing there, and then work out the formula, you can work out what the basal area of the forest is. Now, if you look on your tapes, all I have to do is point out that next to the Master TreeGrower hat, these are made in Germany. So I send over to Germany pictures of the hat, and I say, could you type on this? It says basal area, 2-factor. Now just ignore 4-factor, you won't need that in eucalypts. 2-factor, 49 centimetres. That means that if you hold the tape at the 49 centimetre mark, put that on your cheekbone and hold it straight, let that flop, holding the metal. I know that the little piece of metal there that pops up above the tape is 16 mils wide, and I've worked out that if you count how many trees seem fatter than that, and you've got to do it with the white side up, not the yellow side up, in order for it to work, but the white side up, because that changes, makes this little piece of metal pop up. The Germans didn't know that you could do this with their tape. And you go around and look at all the trees, and if I count 10 trees that look fatter than that, because I'm using the 2-factor, the basal area is 20 square metres per hectare. I haven't touched a tree, and I've worked it out. Then, if I know the height of the tree is 30 metres, on average, I have a basal area of 20, my height is 30, I can work out the volume of wood per hectare, basal area per hectare times the height divided by 3, 200 cubic metres of wood per hectare, and I haven't touched a tree.
Question that always comes up, what happens if the tree is exactly the size of your metal?
There's always a difficult student, isn't there? Okay, this is me looking over the top of the tape in a forest near, just off the highway, and I'm looking at pine trees in a parkland environment. I'm looking down, that's a 16 mil wide piece of metal. That tree is fatter than that, I count it as 1. Then I swing around and I look at another tree. In fact, I'm looking at all those trees and they're all smaller than that. I ignore them. They're all 0. Then, of course, as the difficult student pointed out, occasionally you will find a tree that appears to be exactly the same as the tape. You give that a count of a half. Now that sounds arbitrary, but if you're into the mathematics, in the book, The Farmer's Forest, that we wrote for the Master TreeGrower program 20 years ago, which you get an electronic copy of, it actually explains why it works, why the mathematics works, and that's the brilliance in that guy who worked it out originally. So this just shows the eye, the gauge. All I needed to know was how thick that was, 16 mil, how far that had to be away in order to give my metric 2-factor wedge, because I'm working out metres squared per hectare, and then I look at every tree at about 1.3 metres above the ground. If the gauge is thinner than the tree, 1. If it's the same, half. If it's bigger, 0. And I'll do this in the forest.
And it only works when you really stand still at the same spot.
Oh, you can't. Actually, often when you're looking at a tree over there, it's blocked by another tree. You can move sideways, but then move back. Because if you move sideways and sideways, you're going all over the place. Keep the distance away from the tree even. So it's a little bit of magic, but it's a really useful tool. And if you see a hire car parked on the side of the road in Queensland, and some guy jumping out with a tape over a fence into a forest, doing this, it's probably me. I've measured basal area in all sorts of forests, because I measure the basal area, I measure the diameter of the dominant trees, and I start thinking, this could do with a good thing.
How far back do you measure? Like, so you're in a complex.
Every tree you can see. Because you can imagine, if you're thinking about this as an analogy for what would happen if I planted a tree at this spot. Would it be in competition? dominated by the trees around it, or would it be quite happily growing in a nice sheltered environment? Now, if I have a tree, just 10 centimetres, a small tree, but it's only a metre away from where I'm standing, that little tree can compete with this tree here. A huge red gum, or sugar gum, 30 metres away, could actually be competing with this. It actually works. I'll show you in the field that it's a very good judge of how big a tree is and how far away it is.
I was just going to say, because the further they are, that
Yeah,
They're smaller.
They get
smaller
smaller.
they,
But if they're big enough, they'll still be bigger than that.
Okay.
I think to myself,